welcome everybody. Welcome. My name is Alan Lee, and we are going to be talking hardware today. So this morning, Ben had a presentation on hardware that unfortunately I wasn't able to make. But just from this tweet, I figured with that big slide saying "just don't," I figured, well, that just about sums it up. So thank you everybody for coming to this talk. We'll be done. Just kidding. So today we are going to be, of course, talking about hardware, and more specifically, we're going to be talking about building digital audio hardware and firmware. And I'm going to be going through the basics for building these devices. So these devices are going to look a little bit like this. There's usually a combination of audio inputs and outputs, and then also there may be a combination of data inputs and outputs. Some examples of these devices can include guitar pedals, audio interfaces, synthesizers, and even to a lesser extent, MIDI controllers. And so in this talk, I'm going to split the talk into 5 main sections. I'm going to start off by talking about hardware. And we'll start by talking about some of the basic building blocks, basic circuit building blocks that are in these devices. From there, we'll move on to talking a little bit about the physical implementation, where we talk about schematic and PCB layouts. After that, we're going to be moving into firmware land. And I'm going to touch on a few topics for architecture that particularly pertain to audio. After that, I'm going to talk about a few tips for audio processing, writing audio processing code, especially in a bare metal context that is very resource constrained. And then the last thing we'll talk about today is just a few bits of debugging and profiling bare metal code. What not to expect. So in this talk, we're not going to be talking about building analog hardware, unfortunately. So there's nothing on oscillators or filters. That's going to be out of scope for this talk. And this talk is not a comprehensive guide to hardware and firmware development. A lot of the topics that I have listed here they're really huge fields of study in their own right. And as much as I would like to talk about everything involved in developing hardware, stuffing that into a 50-minute talk is certainly not practical. So there's going to be a lot of things that we're going to be covering. I'm not too sure if we'll finish, if we'll have a Q&A session, but please still, if you do have questions, please still ask them and I'll try to answer them in the Discord. So a little bit about myself. My background actually is not in audio, rather it's in developing calibration and test systems. That's where I got a lot of my electronics and software knowledge. These days, I consider myself as an independent audio developer where I'm focusing on projects that have to do with spatial audio and bare metal audio development. And just on the right, here's an example of a spatial audio plugin that I made last year, which is actually in need of some TLC. It's been quite neglected recently. You can get a hold of me on Twitter at superkittens, or you can email me ali@meowworkshop.org if you have any questions or comments. So a lot of the development processes that I'm going to be talking about today are going to be centered around a recent project of mine that I called Bitmasher. And instead of trying to describe that in words, I'll just let this video do that for me. All right, so that was Bitmasher. It is a audio effects device. A lot of the UI is definitely heavily inspired from retro games. And so in the video, you would have seen the different scenes, and each scene is attached to a particular audio effects. And that includes things like filters, a revolving loudspeaker simulation, bit crusher, tape playback simulation, or as best as I can make tape playback in a real-time system, and a granulizer. So the reason I chose to use Bitmasher as a driving example for this talk is that the architecture of Bitmasher is actually a relatively simple example of the foundational architecture that we see in a lot of different products out there. And that's going to look a little bit like this, where at the center you're going to have some processing and a audio layer which sends off the data for processing. And then there are going to be some peripherals around, which will be different depending on the product. And those peripherals can include things like SD cards, displays, MIDI signaling. And so the specific implementation details, the specific architectural details are going to be different depending on the product, but the base is going to be largely very similar. So we'll start off by talking about the hardware. So this is the block diagram for Bitmasher. It's quite simple. And at the center, we have a microcontroller unit, the MCU. And that basically takes in data and outputs data from its surrounding subsystems. Starting from the left, we have the audio I/O, and the job of that is to digitize audio signals and ship the data off to the microcontroller and vice versa. At the bottom, you have communications. Bitmasher has a USB connectivity option. And right now I'm just using that for firmware updates, really. We have a display, the LCD screen, that shows us the gameplay graphics. User I/O is the buttons, the D-pad, A and B buttons. And then finally we have the power section, which powers the subsystems. So in the interest of time, I'm going to focus on the three main parts, starting with the microcontroller, the MCU. So this is going to be the brains of your audio hardware. This is where a lot of the audio processing will likely happen. MCUs typically consist of a CPU core with a variety of peripherals stuffed into one package. And on the right diagram here is a high-level block diagram of the EFM32PG12 family of microcontrollers from Silicon Labs. And this MCU has a ARM Cortex-M4 core. And at the bottom, we can see a list of the peripherals that Bitmasher may or may not use. Compared to the modern x86 counterparts, MCUs are laughably underpowered, but for a 40 megahertz system like the MCU in Bitmasher, there's an amazing amount that you can do with it. So one of the challenges of working with microcontrollers is that there is a huge variety of them out there. And so just finding the right MCU for your application can be a pretty difficult task. So this table shows us a small list of criteria, certainly non-exhaustive, that one can use to down select the choice of microcontrollers out there. Starting with architectures, MCUs typically come in flavors of 8, 16, or 32 bits. 32 bits are particularly well suited for audio applications. Peripherals, so a lot of microcontrollers will typically have a standard set of peripherals, but there might be a specific peripheral that you might need. Like in Bitmasher, at least in the prototype version, I needed a digital to analog controller, which isn't seen in a lot of microcontrollers. So the Silicon Labs one was perfect for that. For memory, a lot of audio DSP routines will take up a lot of RAM. So having a MCU that has a lot of internal RAM inside is going to be really handy. Power is a big one. So if your project is battery powered, if it's portable, I would consider using one of the low energy microcontrollers. Availability, especially in this day and age where finding chips is increasingly difficult, you want to make sure that the part is easily available. And if you have issues with your microcontroller, having good vendor support, having an active forum that the manufacturer will respond to in a timely manner will help a lot. And then finally, there's the issue of cost, which I don't really think I need to get into too much. So that's all I really want to talk about for the microcontroller bit. Moving on to the I/O block, the audio I/O block. This block is responsible for converting the analog audio signals into the digital domain and vice versa. So you have an analog audio input which gets digitized, and that digital signal gets passed off to some DSP routine, and then that process signal needs to get converted back to an analog signal. And so there's a variety of ways to implement this chain of events, this conversion. And one of the ways is to use a dedicated converter. And this diagram here, just we're going to go through how these things are typically wired and how they communicate. A lot of chips out there will actually combine both functions, and that's what we typically call audio codecs. And so if we look at this, if we look at this example, the way things usually work is that you have an analog input and output. And then the digitized audio signals will typically get sent to the processor, usually through I2S, which is sort of a modification of the SPI protocol. And then the codec itself may have configurable registers or configurable features. And so to control the codec from the MCU, that's usually done through I2C or SPI signaling. The one thing that I want to note for this main clock signal, though, is that a lot of audio codecs will not generate this clock signal itself. It will typically depend on an external oscillator, or you can even use your MCU to generate that clock signal. We're going to see the I2S signaling in action in a later slide. So like the MCU, there is a large variety of codecs out there. And a search for a codec on DigiKey yields about 900 some results. So these are some of the criteria that you can use to narrow down your search. Include things like bit depth, the sampling frequency, power consumption, especially for portable devices, dynamic range, noise performance, and of course availability. Okay, so using a dedicated converter is certainly one option, but another option is to actually use the internal converters in your MCU. And so this is a pretty cheap and convenient option that you can go with, but there are a couple of problems that you need to be aware of. First of all, the bit depth of these converters are usually not sufficient for high quality audio applications. A lot of MCUs that I've seen out there have anywhere from 10 to 12 bits of converter resolution. And then the other thing is that you might need to have some external circuitry for this conversion system to actually work. In the case of the DAC, there might be some high frequency components that might be present, and so you'll have to add a low pass filter to remove those. For the input, you may need to have an anti-alias filter and biasing, and we're going to get into that in the next slide. So for the anti-alias filtering, if you remember from sampling theory, any frequency components past the Nyquist frequency will get aliased back into the passband. Excuse me. And so to remove those components, we will typically use a low-pass filter that we also call the anti-alias filter. And so conveniently for us, there are a lot of really good design tools out there that will do the design job for us. And this example is my favorite one from Analog Devices. And really all you need to do is pass in the cutoff frequency and then the stop band parameters, which you can calculate from this formula. And so the stop band attenuation basically just refers to the fact that frequency components past Nyquist don't register more than one LSB on your converter. And the good thing about this tool is that once you've locked in your parameters, it will generate a circuit for you to implement. And so there are a lot of filter topologies out there that you could use. The sailing key filter tends to be a pretty popular option. And the other thing that I want to mention for ADC inputs is that audio signals will typically have positive and negative values. And that's what we call dual rail circuits. But the problem with a lot of internal converters is that they will actually not register negative circuits. They'll just get clipped to 0. And so to get around that problem, typically what you will have to do is to introduce what's called a biasing circuit. And here I have a simple voltage divider. But basically what happens here is that the most negative value will be changed to 0. And so you have the full range of that audio signal. So onto our last block. This is the system power. So there's a couple of things that you need to consider when designing the power system of your device. First of all, how is it going to be powered? And in Bitmaster's case, there's actually two power sources. It's normally powered by two AAA battery cells, but then if the user connects a USB cable to the device, then it's going to draw its power from VBus. The other thing to consider is what the power needs of your different subsystems are. So in Bitmaster, the MCU and the codec need 2.5 volts, and then the display actually requires 3.0 volts. And we'll get into that a little bit later. So since Bitmaster is battery powered, I figure it would be worth talking a little bit about battery chemistry. For portable applications, alkaline and lithium polymer batteries, LiPo batteries are popular options. Alkaline batteries are great because they're very widely available. They do have reasonably good power density, but the problem with them is that you can't recharge them. But that's where LiPo batteries can come in. They are rechargeable. They have really good high power density, and they come in many different form factors. But the drawback to them is that if you don't handle them carefully, then they can become particularly dangerous. I'm sure many of us have seen those YouTube videos where people have punctured holes in lithium batteries, and it didn't turn out too well for the battery. So when designing the power system, one of the things to consider in the design is how long you expect the battery to last for your device. And so to get a good estimate of that figure, you will typically need to use what's called the battery discharge curves. Some manufacturers may supply them, some may not, and unfortunately in the latter case, you may have to do the measurement yourself using some special tools. But the main thing to consider here, this graph here shows us a discharge curve, a series of discharge curves for a Duracell copper top AAA battery. One takeaway here is that the battery voltage does not stay constant over time. It will go down as the battery is used. But also the rate of that the voltage drops is also not constant. It varies with how much current you're drawing. So to estimate how long Bitmaster is going to last on a fresh pair of batteries, I first need to know what the current draw is. And at full operation, it's about 20 milliamps. And I also need to know the minimum voltage that the device needs, in which case for Bitmaster it's 2.675. And since we're using two batteries, divide that by 2, we get about 1.3 volts. So we draw a line at the 1.3 volt mark. And then since the device draws about 20 milliamps, we can use the 25 milliamp curve, and we see that it takes about 13 to 15 hours for the battery to become useless. Can I do better in terms of power system design? Yes, definitely. I don't think we're using the full capability of the battery, but this is just one way to estimate the life of your battery. Okay, so the second part of the power system design is considering your subsystem power needs. So very likely your subsystems will expect a constant voltage source and also a constant current sources. There are two main types to be aware of. The first one is linear regulators. These are really simple to understand and even simpler to implement. And they're particularly great for analog circuits because they output very clean voltage, depending on your power source, of course. The drawback to them is that the output voltage will be less than the input voltage, and there is a minimum voltage needed for the regulator to operate. And to calculate that voltage, you need to take into account the dropout voltage figure. So as an example for Bitmaster, since it draws about 20 milliamps at 2.5 volts, we can look at this table. We can go on the conservative side and look at the 50 milliamp figure. And so the minimum voltage that we need to input is going to be 2.5 plus 0.175, which gives us the 2.675 volts that we saw earlier. So the other kind of regulator to be aware of are what's called switching regulators. And compared to their linear counterparts, they are very efficient. And even better, they have buck and boost options. That is, the output voltage is greater than the input voltage. The drawback to them, though, is that because they are switching regulators, they can be noisy. And in this oscilloscope's capture, here, I'm probing the 3-volt line. of Bitmasher, which uses a switching regulator to power the display. And we see that we have ripples that we need to filter out. On the left here is a suggested PCB layout guideline from Texas Instruments, and so it's worth noting that it's important to lay out these components properly and also use the right components, because if you don't, then you can have stability issues or even EMC radiation issues, which can affect your chances at passing FCC or CE certifications. So it's something to be aware of. So when calculating when designing the power system of Bitmasher, I take into account the three main components. The three main drawers of power. So there's the MCU, which expects a 1.8 to 3.8 volt, and it will draw at least 5 milliamps, but that's with no peripherals, very likely, and actually in real life, it does draw more current than that. On the codec end, it expects anywhere between 1.8 to 2.63 volts, and I expect it to draw about 11 milliamps of current when I'm in stereo mode and having a headphone output. And these are values that I get from the data sheet. And on the display end, we have a requirement of 2.7 to 3.3 volts, but it doesn't draw too much current, which is quite nice. So for the MCU and codec, I decided that we need at least a 1.8 volt regulator that's capable of at least 16 milliamps. And here I decided to use a linear regulator because we are working with analog components. On the display side, since the display is the only component that's using 3 volts, I figured, and also because the battery voltage does not stay constant as it's used, we're in need of a buck and boost regulator, so a switching regulator would be perfect for that. Okay, so on to the final topic for hardware. When it comes time to lay out your circuit and your PCB, the software used to do that is typically what we call electronic design automation tools, or EDA tools. And the price of such software can range from free, like KiCad, which is what I'm using here, to really, 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 really expensive. But those really expensive tools will often feature like simulators and stuff, and they're typically used for designing high-speed circuits or radio frequency circuits. Before starting out with the schematic capture and designing your circuits, often a big question that you might ask, especially when dealing with a component that you're not familiar with, is where to start with the design. And so this is where manufacturers' reference designs will come in really handy. Typically, they will supply these reference designs in their data sheet or through a separate application note, and they are a fantastic starting point for your design. I want to touch on a couple of tips when it comes to schematic layouts. The first one is read your data sheets, please. And to give a case study here, the EFM32 offers I2S functionality through their serial modules. And the microcontroller actually has multiple modules. But I2S is not supported on every module. So if we look at this table here from the datasheet, we see that Module 1 and Module 3 support I2S. But guess who decided that it would be a good idea to try to implement I2S on serial Module 0? And so, of course, I had to do some reworks. And so that brings me to my next point, which is when you're designing a board, especially the first iteration of your board, do use test points. They will save your life and make debugging and verification so much easier. And when it comes time to manufacture your board, if you are using an automated test system, typically the point of interface between the test system and your board is through these test points. Another recommendation that I'm making here is that if you have any unused pins in your MCU, I suggest breaking them out into test points because you might never know when you'd need them. And I personally, for Bitmasher, ended up using them when I blendered my I2S implementation. Okay, so for PCB fabrication, a big thing to be aware of is that your manufacturer is going to have a set of tolerances. And typically they'll post these on their webpage. And I highly recommend transferring these tolerances to what's called a design rules checker. You'll find them in practically every EDA tool out there. And so before you send out your board to the manufacturer for fabrication, it's good to run this design rules check just to make sure that your board is manufacturable. One thing that I want to note here, if we look at the trace spacing as an example, the manufacturer says that they are able to handle 6 mils. But just because the manufacturer says they can doesn't necessarily mean you should test them to it, unless you really have to. So what I would do is add a little bit of margin on top of this tolerances. So having a spacing of 10 mils would probably be a good idea. Okay, so since Bitmaster and audio products are likely going to have a mix of analog and digital circuits, this brings us into the mixed signal domain. And so when that's the case, the placement of the components becomes very important. And grounding becomes especially important because improper layout of your grounding or improper placement of your components can cause a switching noise, which can wreak havoc into your analog circuit system. And that actually happened to be the case in Bitmaster with one of my revisions of the board. When I was listening to the audio, I noticed that there were some clicking noises in there, and that's what this oscilloscope probe shows. So every 33 milliseconds or so, there are these strange click sounds. And so it turns out the root cause of that was actually from the display SPI lines, where every 33 milliseconds, since the display is running at a frame rate of 30 FPS, data gets sent over. And so that noise, that switching noise, was actually getting coupled into analog lines. So one of the ways that you can mitigate this is to use ground planes. I highly recommend using at least 4 layers for your design. Ground planes are great because they offer a short return path for your current, hence lowering the distance that current has to travel, and that just reduces noise and EMC emissions. And so just to give an example here, this is a plot of the audio output for a 2-layer board. It's what we saw on the oscilloscope in the previous slide. And so with a 4-layer board, this is the audio output. So those clicks were effectively gone. There's one thing that I do want to mention about grounding, though, is this slide made it seem really easy, and I highly recommend using ground planes. But the problem of grounding is actually really, really difficult. And just because one fix solves one particular scenario's problems doesn't necessarily mean it will fix a different scenario. So thankfully, there are a bunch of resources out there, but this is one thing to consider. The other thing that I want to talk about in terms of signal integrity is bypass capacitor placement. And bypass capacitors are effectively power sources that supply power on standby. So if a chip has a sudden need for power, then instead of getting it from the power supply, it can get it from the bypass capacitor instead. But it's really important that these capacitors are placed as close as possible to the chip pin, because the further away it is, the longer the trace is going to be, and the longer the trace you get, you have a greater inductance, which effectively means you have an antenna and you have greater risk of EMC emissions and also noise coupling into your analog lines. Okay, so last thing that I want to talk about for hardware, soldering. So for home prototypes, there are 2 popular methods, the hand soldering method and reflow soldering method. So for hand soldering, you would use like a soldering tool to attach components on. For reflow soldering, typically you would have a stencil and you would apply solder paste using that stencil, which is what I have on the right here. And then you would put this through a special oven where it would melt the solder and attach components. It turns out that reflow soldering is a popular method for manufacturing. So if you do plan on manufacturing your board, I recommend using SMT components versus through-hole components. Okay, so on to the firmware part of the talk. So before I move on, I just want to shout out 2 talks at last year's ADC. In this talk, I'm not going to go through the basics of bare metal programming, but so I'm going to assume that you know what interrupts are and what memory mapped registers are. But in case you don't, I highly recommend watching these 2 talks. They give an absolutely amazing overview of the landscape of embedded programming. So to start off the architecture discussion, I just want to go through the data flow of audio or the audio data flow between the MCU and the codec. So imagine we have a output buffer of samples that we want to write to the codec. And so to initiate that transfer process, we would transfer the sample into the I2S transmit buffer. And that I2S module is going to initiate the transfer. And so on the codec side, we'll have the SD in the serial data in port that receives the data. And then there's your clocking and then a left-right channel clock. But at the same time, the codec is going to send out an audio sample to the microcontroller. And so that gets entered into the receive buffer, and we are responsible for writing code that will transfer that sample into some input buffer. So that was for the left channel. The same thing happens for the right channel. So we write that into the buffer, it gets sent out. And also notice that in this case, the right channel, the clock signal, LRCK clock signal, is high to indicate that it's the right channel. We get a sample from the codec, and then that gets written into the buffer. So programming-wise, this is what the sequence of events is going to look like. So suppose we are just running through some normal program execution, and then at this point we decide to initiate the transfer process. So here we write a sample into the transmit buffer, and then the I2S module will send and receive samples asynchronously. And then once that sample gets received, an interrupt would get triggered. And so this is where we transfer the received sample and then add the right channel sample. And the process repeats. We get an interrupt, and we shift in samples again, and the process continues. So the one interesting thing to note about this sequence is that there is a pretty high frequency of interrupts that's happening. And so if your I2S module was the only module that was generating interrupts, then that actually might be okay. But in Bitmaster's case, there's a lot of different things going on. And so having this high frequency of interrupts might actually run the risk of starving other tasks from ever executing. Things like the display and game updates, and also the audio processing. So one way to get around that is to use what we call direct memory access. And in the previous example, we actually relied on the CPU to handle the transfer of data from memory to peripherals. But we can delegate that to a direct memory access module instead. And so this would handle the transfers in the background while the CPU is free to do whatever it needs to do. And so typically, the way that DMAs are configured are that you specify where the data is going to come from, where it's going, and also how many data points that you want to send. So this time, if we look at the sequence of events, we have normal execution, and then here we decide to start the DMA transfers. Let's say we want to send 512 samples. And so that transfer will happen in the background, and the CPU is free to do whatever it needs to do. Once the input buffer is full or the output buffer is empty, interrupt gets triggered, and we set up the DMA module for the next sequence of transfers. And so there's a lot more time that the CPU has for processing and handling other tasks. So speaking of tasks, Bitmaster has a lot of different tasks that it manages. There's audio processing, there's game updates, there's display writes, I/O handling. And so one way to manage all of these tasks, Bitmaster uses a really simple approach. I use what's called a task queue. And this is really part of the multiple producer, single consumer model. And so for example, if we have an event where the DMA input buffer is full or the audio input buffer is full, then in the ISR, there would be an audio message that's sent into the queue. Likewise, if the display update timer expires, that is, the display needs to be refreshed, an update message gets added into the queue. And so in this loop, it will get the messages from the queue, and it'll process the messages, or it'll start processing based on the message that it gets. So in the case for audio, it will run it through audio processing. And in the case for updates, there's actually a few things that happens. It handles the user I/O button presses, it'll update the gameplay, and it will draw to the frame buffer. So since this is an audio device, since it's a real-time audio device, there are some timing constraints that we need to consider. And there are a lot of the tasks we need to complete the tasks without interrupting the audio portion. And so there's a number of ways to solve this problem, but Bitmaster takes a really basic approach, and that's where I take a look at the task that has the highest bandwidth. So in the audio case, a new buffer of output samples is expected every 32 milliseconds. And in the display update case, we refresh the display every 33 milliseconds. And so audio has the higher bandwidth. And so what I do is I have a maximum time that all tasks must finish by. And so in this case, I have a 50-50 ratio, but you can actually have any ratio as long as all of those tasks finish within the prescribed time. Now, if you have a particularly complex system, then I would actually recommend looking into real-time operating systems or assigning priorities to tasks. And if a higher priority task appears, then that would preempt a currently running lower priority task. But there are, of course, some difficulties associated with that. But what Bitmaster uses is very basic. If you have more complicated stuff, there are other techniques out there. All right, to the audio processing portion. So these are just a few things that I wanted to mention when dealing with audio processing. A lot of MCUs will not have a hardware accelerated floating point unit. And so if you wanted to work with floating point numbers, you would have to do that in software. And that's going to increase your execution time, audio processing time by a lot. And so one way to still have fractional representation is to use, without using software libraries, is to use what's called fixed point numbers. And in this example, I have a Q1.15 number, which basically means that it's a 16-bit number where 15 bits are reserved for the fractional bit and 1 bit is reserved for the sign. But there's a couple of things that you need to be aware of. First of all, you can run the risk of overflow when you're running arithmetic operations. And then the second thing to be aware of is that depending on how many bits that you use to represent fractional bits or fractional parts, you will definitely have some loss in precision there. So those are the two things to consider. For the ARM Cortex-M4, and I believe other ARM processors, ARM actually has a DSP library that you can use. And this library has functions for accelerated maths, trig functions, even filtering functions. And so these can become really handy when you write your audio processing code. Interestingly, the M3 and M4 processors have limited SIMD options, but unlike the x86 counterparts, which have upwards of 256 to 512 bits where you could stuff variables in, the Cortex M3 and M4 offer only 32 bits, so it's not very useful for floating point numbers, but it is very useful for fixed point numbers. And so this just illustrates an example of where I use SIMD. This is an example of a Schroeder reverb, and the topology has 7 comb filters which have their own delay lines. And so typically, when you're writing an update function, you're going to have code that looks like this. You're going to have an index. You're going to have to update an index where the sample gets shifted in and out. And so this piece of code would have to get executed 7 times for each comb filter. But we can actually halve the number of operations by using SIMD. And so the way that would work is the index would have to get converted into a 16-bit number, and 2 indices can be stuffed into one 32-bit variable. And then you would call it the SIMD subtract function, and then you would have the updated result of the indices in one go. There are, of course, other things to consider, namely what to do when the index needs to wrap around. And there are, thankfully, some SIMD instructions that you can use to solve that problem. But I'm not going to get into that for this talk. So just to compare the performance gain, so if we went with updating the index for every comb filter, that would take about 3.74 milliseconds for a buffer size of 1024 samples, and with optimizations enabled. With SIMD, we get a processing time of 2.86 milliseconds. So it's not insignificant. I also do want to note that you can use SIMD for the actual data calculations, like for your audio output. But I would be careful with that, because just because you can use SIMD doesn't necessarily mean that you should use. And it might turn out that SIMD code that you wrote might actually be slower than the scalar code. that the compiler would optimize. Okay, so finally, last thing that I want to talk about, hardware and debugging. So when working with circuits, a good multimeter is an absolute must. And if you're working with analog circuits, or really just circuits where things are changing, which basically is every circuit, I highly recommend getting an oscilloscope. And if you're also dealing with digital signaling, I recommend getting a logic analyzer, although an oscilloscope can do the job of a logic analyzer. But these three tools will really help you when working with hardware, and I highly recommend getting them. Okay, last thing. So profiling code. So profiling bare metal code, there's a few ways to do that. One very simple way is to simply just toggle a pin and connect a oscilloscope or a logic analyzer to them. And so in this example, I just set a pin high before I enter into the code in question. And then after it's done processing, I call clear. And so looking at the logic analyzer output, I see that the code takes about 6.3 milliseconds. Thing to be careful of when using this, if you are using a high-level abstraction library to toggle the pin on or off, you need to be aware of some extra code that function might be calling, and so that extra code might be introducing some latency. Another option is to use a hardware timer. So if you have no GPIOs available, you can use if you have any free timers, by all means, that's another option. And so here I'm just setting up a timer, and then I initialize the timer or start the timer before I enter into the code. Once it's finished, I disable it and I read what the counter value is. But be careful that the timer does not overflow. And I recommend adding an interrupt routine that keeps track of how many overflow events happen to get a more accurate idea of how long your code takes. And then finally, this applies to the Cortex M3, M4, and M7, I believe. And manufacturers actually may or may not choose to implement this particular module. But this is the data watchpoint trace module. And in this module, there is a counter that you can use for that basically acts as a timer. So it's very similar to using the hardware timer method. So here I enable the counter, and I go into the code in question, and then I read the counter value. So just like the hardware timer in the previous slide, you do have a risk of overflow, and so it's good to keep track of that. So that's everything. That was a lot, I understand. So some final things that I want to say. There's a lot of steps involved in building audio hardware. And if this is your first time building hardware, I recommend that you start small. Start with basic circuits and basic PCB designs. There is no shortage of good resources out there on the internet for building hardware. Arduinos offer a good introduction into bare metal programming, and even these days with the introduction of the Electrosmith Daisy, that's also a good platform that you could use. So yeah, start simple and then build your way up. This is a list of resources that I've compiled that you can reference. They've helped me in particular. And that brings us to the end of the presentation. Thank you everybody so much for listening.